topic is probably more related to the confidence, so that's why I actually switched that. Okay, so let me go quickly to that. Okay, so this
20
is
minutes including questions.
okay, very good. So Taka's phase diagram. What I want to point here is that there are so-called critical points around here where the claim is that there is a transition from nodeless to nodal. Another point I want to make quickly is that in these materials, 3d6 iron orbitals are important, and this dxz, dyz orbital are degenerate, which allow, and also half field, which allow to have the fluctuation of density. And then there was a whole discussion, what is the other parameters here, that some simple combinations are proposed, but it's not limited to that. All right, so I mentioned about this dxz, dyz orbitals. In this so-called nematic phase, the other parameter is the difference between this occupancy, and that leads to simultaneously change of the Fermi pocket, so the circular becomes C4 breaks if one gets occupied more than others, so this is Pomerantsev type transition. And lattice couples to that, so lattice actually knows about that, so there is a broken symmetry both in lattice and electronic response. And well, there are some quadrupole lattice distortions associated together with electronic fluctuations. There's also always question what drives this transition, nematic transition, what is most responsible, is this effect of electronic, is the effect of spin, is the effect of lattice. And experimentally, so this is the focus, this is why I wanted to put this in contents of this conference, is that this quadrupole response can be measured actually experimentally, as far as I know, by 4 ways. So one way is the work that we do is by Raman scattering, and in this case we actually measure the dynamics of the fluctuations, and from that we can extract the static part as well. The second approach is elastoresistivity, pioneered by Ian Fisher in Stanford. They measure, of course, the static part of it, but it looks very similar from what we can extract from dynamics. The third approach is elastic modulus, here pioneered in Karlsruhe at some point already 10 years ago or more. And then the result and good NQR measurement, where you couple to nuclei and then measure NQR relaxation time. And all 4, well, in this case, give more or less consistent results, you can see. So this is the limit, what can be done, and of course, most of these probes, almost all of them, are Q=0 probes, so they really measure only for gamma point, and if it happens, instability happens at finite Q, then well, inelastic X-ray need to be approached, and so on. Okay, so it's universal phenomena, so it's across all the compounds that I showed in Taka's phase diagram are present. There is no exclusion, so almost. And okay, very quickly, so what we can do in Raman, we employ a polarization result measurement where we can polarize the incoming and scattered photons relative to the lattice, and from that we can basically tell what is the symmetry of the excitations, and turns out that this XZ, YZ fluctuation all appears in this B2G channel, And this is where, in Raman response, well, this is B2G channel, this is some other B1G channel, and you can see that above nematic transition there is broad feature, which is kind of softening towards cooling, and then the transition happens. The nematic gap opens up, and so this condenses, and this fluctuation gets away. And well, and from this data, dynamic data, one can calculate straightforwardly the static susceptibility, and it looks like that, and where static susceptibility looks like that. So it points towards critical temperature. So this is a kind of standard analysis, and it can be applied to 1 to 2 various materials. They all give the same results. So I'm just flashing results over a decade of data. But now let's talk about superconductivity. So what happens if this nematic state enters the superconducting state? And there's several possibilities. So when we enter the superconducting state, so this is the energy of the gap. Let's see what happens with that. So we had very overdone fluctuations, which was a broad feature, and when gap opens up, it becomes a very sharp in-gap resonance. So it's a collective mode. This collective mode has this XY symmetry, B2G on square lattice, and in this case, it stays at the same resonance, and this is S plus minus superconducting. So it's not in the yellow range of this Tapas phase diagram. You can vary the doping, and I mean the strength of that resonance is changing. The position is barely changing, but that's what it is. So this is that resonance. This is the gap. And this resonance is essentially a collective state in the gap, which exists as a damped feature above the transition, nematic transition, and becomes a sharp feature below the superconducting transition. So the superconducting state is a sharp. Okay, so now let's talk about other cases. So that. Let's go to this material, which is on Tapas diagram going this way. So this sample is a 0.6, it's here. And this is the collective mode, this is the gap, this is the collective mode, this is the gap on other pocket. And it's very clearly seen here. So question is what would happen if we dope that sample further. So this is the collective mode, its dependence of doping. So we had samples here, here, here. This is how it behaves. Unfortunately, any sample that we had at high doping didn't show electronic response. The samples are just too messy to do their measurements, because the question really is, and this is point of interest of this conference. The question is whether this softens and the superconductor becomes a D-wave superconductor, because this quadrupole mode condenses. We were able to do the measurement better on this material, which is now doping along this line. And here, when we approach this point, we clearly see the softening of the collective mode. So this is the collective mode, which is the lowest energy, which softens. The next feature is related to the gap, but we can see that it does soften. We had no luck with samples in the yellow region to check whether those are really D-wave, but there is certainly a tendency, at least in that direction, to condensing of this nematic collective mode towards making it a D-wave superconductor. All right, so is this okay with time?
That's just perfect. Thank you
Okay.
very much.
Yeah.